Hello all. Today we will see new topic related to the multitasking unit, that is TSS descriptor. In the previous lecture we had seen what is the TSS segment, that is the task state segment and its different fields. So let's start. Like other segments, the TSS, that is the task state segment, is defined by the descriptor called as the TSS descriptor. Now, like other segments means what? The code segment, the data segment, the stack segment, like how these segments they require or they are defined by the descriptor. Similarly, the task set segment is also defined by a descriptor called as the TSS descriptor. So this is the following figure that will show the diagram of a task state segment descriptor, and its fields are nothing but somewhat similar or like other segment itself. So this diagram we had seen in the previous unit also. This is nothing but a 32-bit TSS descriptor. It is containing of base 16 to 23. Then the next field is the type field. It is having bits 1, B, 0, 1, 0. Then it is having the bit as DPL, that is descriptors privilege level. P bit is nothing but the present bit. And over here, B bit is representing your busy bit. Then is the limit field from 16 to 19. Then we have the AVL, that is nothing but telling you the availability of the operating system or availability of the particular field. Then is 0, 0. Then granularity. The granularity bit, or it is nothing but telling you, or it is used for specifying the units with which the limit field is interpreted. It is mainly associated with the units, and that units are telling you the that how much the limit field is interpreted. Okay, so when this bit is 0, the limit is interpreted in units of 1 byte. Otherwise, the limit field is interpreted in the units of 4 kb. Okay, so G bit is very important because it specifies the units. Next is the uh, again we have base 24 to 31. In the below section, we have segment base of 16-bit and segment limit of 16-bit. So let's see the further points. The B bit in the type field indicates whether the task is busy. See, this B bit will indicate whether the task is busy or not. Whatever the task is assigned to the processor, whether it is currently busy or not. So this bit will indicate. Then tasks are not re-entrant. I repeat again, re-entrant. Now, what is the meaning of re-entrant? Re-entrant is nothing but it is used in with terms of a computer program or a subroutine. Suppose if a computer program or subroutine is called re-entrant if multiple invocations can safely be run concurrently on a single processor system. Means what? Multiple invocations means multiple calls. If there are multiple calls, and if a single processor it can handle that multiple calls concurrently, then we can say that particular computer program or that particular subroutine is a re-entrant. And also the re-entrant procedure, it can be interrupted. There is these re-entrant procedures, they can be interrupted in between if required, and in the middle of its execution they are having that possibility that in the middle of the execution only we can interrupt this procedures, and then again safely they can go back to their previous invocations and complete that invocation. So this is nothing but tasks are not re-entrant. Over here the meaning is that whatever the tasks are assigned to the procedure, they are not re-entrant. So the bit B bit allows the processor to detect an attempt to switch to a task that is already busy. So as these tasks are not re-entrant, what does the B bit will do? This B bit will allow your 80386 microprocessor to detect, means to find to such a task that is already busy. So first it will find a task that is already busy, and then it will carry on the further procedure. Then next fields are the base, limit, DPL, that is descriptors privilege level, G bit, and the P bit. P bit indicates the present bit. These bits are similar to the other descriptor fields. Then next, the limit field, however, must have a value that is equal to or greater than 103. 103 why? Because your microprocessor, that is 80386, requires minimum 104 bytes of storage in order to perform a context save. So it is the feature or it is the property of 80386 microprocessor that it requires minimum storage of 104 bytes so that it can perform a context save. Context save means what? It is nothing but it is an interrupt. That is the first thing an interrupt does is to save all the intermediary data. So in order to save that intermediary data, your storage should be at least 104 bytes. A larger limit is permissible and is required if only when the IO, that is input output permission map is present. If input output permission map is present, then and then only you can have a larger limit. Okay, so the maximum limit for your task state segment is 4 GB. Then next point, to access a TSS descriptor, the procedure must have privilege level that is less than or equal to the privilege level specified by your DPL field of the TSS descriptor. Very simple. Whatever, if a procedure is trying to access your TSS descriptor, then that particular procedure's previous level must be less than that of the privilege level of the TSS descriptor. The next point, usually this access is restricted for only the trusted softwares. Why? Because whose privilege level is 0. So this can be done by setting the DPL field of the TSS descriptor to 0. So only the trusted softwares have the right to perform the task switching. The softwares that are trusted, that don't have any malfunctions, that means they are trusted softwares. So they have the right to perform the task switching, because task switching is a very important, we can say, topic or important task. Then next is the task registers. The task register, that is termed as TR, it will specify the current executing task by your uh, microprocessor, and it is shown by pointing to the TSS, that is the task state segment. There is a figure that will show the task register diagram, that of task register diagram of 80386, and also it can access the current task. The task register is a selector for the TSS. What is the task register? Nothing but a selector for the TSS. And over here, the selector is doing the task of pointing to the current task that it is performing. Okay. So we will refer the following figure. The third point, it has two fields or it has two portions. Task register has two portions. First is the visible portion, which can be read and changed by the instruction, and the another is the invisible portion. Okay. So what does this mean? That is maintained by the 80386 microprocessor to correspond the visible portion which cannot be read by any instruction. This means what? The visible and invisible portions, they are maintained by your processor in such a way that they can correspond to the that visible portion which cannot be read by any instruction. So it is corresponding or it is mapping with that particular instructions. Then the selector in the visible portion is used to specify a TSS descriptor in the GDT, that is the global descriptor table, and invisible portion is used to cache the base and the limit values from the TSS descriptor. This is the diagram, task register diagram. Whatever the points I have read, I will relate it with this diagram. See, this is your TSS, task state segment. Okay. Then this TR, that is the task register, consists of three fields: selector, base and the limit. Over here, 16-bit field is the visible portion. This is nothing but the visible portion, and the remaining portion is the hidden register. This is the visible register and this is the hidden register. Now, what happens? This is the GDT, global descriptor table, and in the global descriptor table, there is the TSS descriptor, that is the task state segment descriptor. Now, the selector field of the task register is used for pointing to the TSS descriptor, so that it will tell you now currently which task or which procedure it is carrying. So, selector is doing the work of what? Pointing to the TSS descriptor. Then, the base is pointing to the TSS descriptor is pointing to the base field also, as well as it is pointing to the register field, hidden register field of the limit. So base and limit from the TSS are going to the hidden portion, which are indirectly the base is pointing to the TSS segment again, and the selector portion is directly, that is the visible portion, is pointing directly to the TSS descriptor itself, because your descriptor will also have base and limit fields. So accordingly, it will point to the base and limit fields of the task register that is mentioned over here. Then holding the base and limit in the visible portion of the task register makes execution of the task more efficient. What is written over here will relate with the diagram. See, now if you're holding, suppose, the base and the limit, what it will do, what it will make more easy. See, holding the base and limit in the visible portion of the task register. This is nothing but what? Your base and limit in the invisible portion. What it will make, it makes execution of the task more efficient, because I will say again, as their base and the limit is present in the invisible portion, then it will make execution of the task more efficient, because it will correspond to the base and limit of the portions that are not readable by other tasks. So, because the processor does not need to repeatedly fetch these values from the memory when it refers to the TSS of the current task. The very important and main point is that there will be a question in many students' mind, that why this base and why this limit is present in the hidden register. So it's the key answer to this is that, suppose if there is a process and that process is going to get executed, okay, and if it is getting executed, in order to make the task execution or that process execution more efficient or more fast, what the processor is doing, the processor, no, it will not repeatedly fetch these values from the memory. Means what? Whenever that task is called, the processor will not again and again search its base, it will not again go and see what is the limit. So it will so the base and limit are already fitted in the or we can say already stored, and that is stored in the hidden part. And when that particular process is called, so instead of again and again taking the values of base and limit from the stored, that is from the process itself, it what it will do, it will fetch these values from the memory directly. These values will be, as these values are stored in the hidden portion, so the processor, it will directly fetch these values from the memory when it refers to the TSS descriptor. Whenever the TSS descriptor is getting point, the directly it will refer to the memory, and these values will be fetched of that current particular task itself. Okay, so for this, the 80386 is that is our microprocessor. It gives us two instructions. See, the 80386 gives two instructions to read and modify the visible portion of the task. We want to read and modify this visible portion of the task. So what are those two instructions that are given by the microprocessor? They are LTR, load the task register, and STR, that is store the task register. First you have to load it and then you have to store it. What this LTR and STR are doing? It holds the visible portion of the task register with the selector and invisible portion with information from the TSS descriptor selected by your selector. So LTR is a privileged instruction. What is the meaning of privileged instruction? Privileged instruction is nothing but that has the right to access a important what we can say that has having right to access the important task or important procedure or important work. So privileged, so they are called as the privileged instruction. Thus, it is executed only when your CPL, current privilege level, is 0. Okay, so understood what is LTR? It will load the visible portion of the register with the selector and invisible portion with information from the TSS descriptor that is selected by a selector itself. Okay, and LTR is nothing, it is but a privileged instruction and it is executed when the CPL is 0. And what does STR do? It stores the visible portion of the task register in a general register. Whatever is the visible portion. See, this is the visible portion of your task register. So this visible portion is stored in a general register or the memory word. So STR is, it is not a privileged instruction. Okay, it is just a generalized instruction. Now next part we will see, that is the task gate descriptors. Task gate descriptors. Now like the call gate, the interrupt gates, like other gates, this task gate, it is also a special type system gate, special type of a system gate. What it does, it has its own descriptor. Whatever are the special system gates, they are having their own descriptors. So a task gate descriptor does not define a memory segment, but it will instead act as an interface between the user and a task segment. The main point with respect to task gate descriptor is that it is a special system gate. It does not it has its own descriptor. So task gate descriptor, it does not define a memory segment, rather it will act as an interface between the user code and the task state segment. Directly it will be an interface. So it provides an indirect and protected reference to a task state segment. Then the following figure will show the format of a task gate descriptor. A task gate descriptor defines a selector to a TSS descriptor which uniquely identifies a task. It is always uniquely identifying a task. Next, like the selector to a call gate, the selector to a task gate can be used in place of a selector to a code segment. Very important point. Like there is a selector in a call gate, also the selector with respect to a call gate, it can be used in place of selector to a code segment in the far JMP and far call instructions. What is the use of this far JMP and far call instructions? This far jump, it allows to jump outside the current code segment. Whatever is your current code segment, with the help of this instruction, we can jump from outside the current code segment. And what does this far call instruction do? It will refer a procedure which is in different code segment. It will just refer a procedure that is present in the different code segment. So this is the diagram of the task gate descriptor. It is a 32-bit descriptor in which the first 7 bits are not used. Then we have 10100 descriptors privilege level, the P bit, and again the remaining 16 bits are not used. Below is the portion that is having the selector part only, and then the first 16 bits are not used. We'll read now about this diagram. As mentioned earlier, the descriptor's privilege level field of a task gate controls the right. What it controls? It will control the right to use the descriptor to cause a task switch. See, who is causing a task switch? That means what? Anyone cannot have the right to, that means any descriptor will not have a right to cause a task switch. So it is given to some special type of descriptors only. So the DPL field of a task gate is so important that it controls the right to use the descriptor to cause a task switch. Whenever you want to perform a task switch, it should have a right to control the use of the descriptor itself. Then procedure selects a task gate descriptor. There is a procedure, then it will select a task gate descriptor only when the maximum of selectors RPL and the CPL of the procedure is numerically less than or equal to the DPL of the selector. The procedure is selects a task gate descriptor. When it selects the task gate descriptor only when the maximum of CPL and maximum of RPL, current privilege level and maximum of requesters privilege level is less than or equal to the task gate of DPL, that is the descriptor's privilege level. Now, if DPL's privilege level is 0, suppose your DPL is having a privilege level 0, then what happens in that case? Then the privilege level constraint, it will prevent the untrusted procedures. What there are some procedures that are untrusted. Then this privilege level constraints that prevents the untrusted procedure from what? From causing a task switch. In this case, if your DPL is 0, then those procedures that are untrusted, they will not be allowed for task switching. Only the levels that are having the trusted procedures will be allowed for task switching. Okay. And procedures having the privilege level from 1 to 3, it is mentioned in the brackets. But through task gates, we can switch from lower privilege level to higher privilege level. Because when a task gate is used, the DPL of the target TSS descriptor is not used for the privilege checking. Very important advantage is mentioned over here. See, in this point, they have told that untrusted procedures cannot perform task switching. But because of the use of the task gate, if you are using a task gate, we can switch from lower level to the higher level. Why? Because when a task gate is used, the descriptor's privilege level, that is the DPL of the target TSS descriptor, it is not used for the privilege checking. So in that case, the DPL will not be used for checking the privilege, whether it is having same privilege level or whether it is having higher or lower level. So this privilege checking will be not done if you use a task gate. Thus, a procedure that can have access to a task gate has the power to cause a task switch. So whatever the whichever is a procedure that has the access to a task gate has the advantage that it can perform a, or it has the power to perform a task switching. So this is it. Thank you.